We start off our delta x, b minus a over n. Again, a and b are given in the interval. So b is equal to 1, a is 0, over n. We're keeping it as a generic n to apply this limit process. So we get that delta x is b minus a over n, and that gives us 1 over n. Now, for my right endpoint, what I'm going to do is I'm going to plug in a, which is 0, plus I, we keep I as the index, and then our delta x, which we just found, as 1 over n. So if you simplify this, you're really getting that CI is going to be equal to I over n. All right, so now we are going to plug that into our definition of the definite integral using our limit of the Riemann sum. So our definite integral from 0 to 1 of f of x, x squared plus 3 dx, is going to equal the limit as n goes to infinity of delta x times the summation from I is equal to 1 to n of f of ci. And again, we're thinking about this delta x summation of the f's. That's our Riemann sum, and then we take the limit as n goes to infinity. All right, so I plug in what I know, and I know that delta x is equal to 1 over m. And then I have to spend some time thinking about what this f of ci is actually going to evaluate as. So that's kind of where I go off to the side. I always kind of go off to the side for this one. So f of x is equal to x squared plus 3. I'm trying to find f of ci. Now, my f of ci is going to come from the fact that ci is I over n. So everywhere that I have an x, I am going to replace that with I over n. So this x gets replaced with I over n. This x will become I over n quantity squared plus 3. Now, you could just plug that in immediately. What I kind of like to do, though, is simplify it as much as possible off to the side and then go plug it in over here. So if I simplify this, I'll distribute this square to both the numerator and the denominator. So that gives us I squared over n squared plus 3. And there really isn't any other simplification that we can do. So we're going to plug that in for our f of ci. So f of ci is I squared over n squared plus 3. All right, now here is where we have a little bit of a challenge on our hands, because what we want to do is once we plug in the delta x and the ci, we want to get this guy separated so that it's in terms of a number I or I squared, okay? So we have plugged in the delta x and the ci. That's done. Now what we're going to do is we are going to split it up. And when we split it up, the goal is to get it as a sum of either a constant I squared, I cubed, etc. So that's kind of where we're at in this process. So I am going to split up this. And all of this is going to be multiplied by the 1 over n. So I'm going to split this sum into 2. Now, if you look at this first term here, this n squared does not depend on the index I. So that can come out in front. So this 1 over n squared comes out in front. And if I bring the n squared out, then all I'm left with is an I squared inside of the summation. So we have I is equal to 1 to n. Then we have plus. And then here, I'm splitting it up into 2 separate summations. The sum from I is equal to 1 to n of 3. So that's using our constant multiple rule and the sum rule to split it up into 2 separate sums. Now, the reason why we do that is because, again, we want this sum of ci or I squared. So now what we can do is we can plug in our sum rule for I squared, and we can plug in our sum rule for 3 or a constant. So here we are going to use our sum rules, summation rules, and again, those are what are over here, these 4 rules on the worksheet. That's what we're using now. So plugging in, we will have, just for this I squared, it will become n times n plus 1 times 2n plus 1 over 6. That's my I squared plugged in. Okay, but the summation plugged in. But the 1 over n squared is still there. And then here, for the constant 3, we get 3 times n. So again, this summation, when it's evaluated using our sum rules, is going to become 3n. Now, we still have this 1 over n to deal with, and of course, we still have the limit as n goes to infinity. Now, if you look at what we have, though, I really want to emphasize, like if you look at this line right here, The summation is gone. So now the focus becomes on steps 3 and 4 of how do we evaluate this limit. So to evaluate the limit, what we want to get is we want to get a number over n to a power p. So to get to that, we are going to have to simplify as much as possible. So we're going to simplify to try to evaluate the limit to get a number over n to the power p, and then we'll be able to deal, okay? All right, so let's see how we are going to deal with this. The most obvious thing to simplify here is that an n here can cross out with one of the n's here, okay? And inside the bracket, there's really not too much more to simplify. So I have n plus 1 times 2n plus 1 over 6n plus 3n. All right. Now, remember, we want a number times a number over n to a power p. We do not have any interest in having all these little parentheses here. So our next step is going to be to distribute out those parentheses. So again, we're not really interested in all this little parentheses mess. So because we want number over power n to a power, so we are going to distribute here. Okay, so let's go and do that. And I'm going to be honest, like when I did this, I would memorize like what this FOILed out as. You don't have to do that, but that is an option to just memorize the FOILed out expression, and then that saves you a little bit of work. But this is going to be 2n squared plus, be careful with your foiling here, you have an n and then a 2n, so that gives us a 3n plus 1 over 6n plus 3n. And then we have our 1 over n limit as n goes to infinity. All right. Now, we want to have, again, number over n to a power p. So we want a bunch of little terms that look like that. So what I'm going to do is I'm going to split this up as 2n squared over 6n plus 3n over 6n plus 1 over 6n plus 3n. Then that's multiplied by 1 over n. All right, so then I simplify. So the n squared over n will become an n in the numerator, and then a 3 from the 2 over 6, the 3 in the denominator. Here the n's cancel, and I just get 1/2 plus 1 over 6n plus 3n. All right, now we're still not there because yes, it is true we want number over n to a power p, but we do not have that. We have this 1 over n times this expression. So we have to distribute out to all 4 of those terms, and that will give us 1 over n times n over 3 plus, multiplying straight across here, 1 over 2n plus 1 over 6n squared, because I have an n times an n, plus 3n over n. And then looking at the limit as n goes to infinity. All right, then we see that these n's cancel, these n's over here cancel, and we're looking at the limit as n goes to infinity of 1 over 3. Now, if you really think about this for a hot moment, this 1 over 2n, that's going to go to 0. When we take our limit, this is going to go to 0. The 3 is not. So it's going to be plus 3, and then now the limit is gone. So that's how you can kind of simplify it quickly there. And then, of course, you got to take your 1/3 plus 3, so you get your little common denominator, and you have 9 plus 1, so you get 10/3 as your evaluation for that limit. Now, again, don't lose sight of what you have just found. You have found that the integral from 0 to 1 of x squared plus 3 dx is equal to 10/3.